For decades, computers operated on a strict exchange. Programmers had to write explicit, step-by-step instructions for every single task a machine needed to perform. Take a basic spam filter, for example. To stop junk mail, engineers had to manually script exhaustive if-then rules. If an email contains suspicious words, or if it has unusual links, then route to the spam folder. But the modern internet generates billions of chaotic, unpredictable data points every day. Human programmers cannot anticipate or write rules for every possible variation of spam, let alone the infinitely more complex data of the real world. Reaching this ceiling forced a shift in methodology. Instead of programmers defining the rules, they began building systems that could study millions of examples to find the patterns themselves. Rather than trying to write the rules themselves, engineers decided to build systems that could figure out the rules on their own. They structured this approach around a neural network, an architecture that loosely mimics how biological neurons inside a brain learn from experience. Dropping strict programming instructions in favor of a biological trial and error process gave machines the flexibility needed to finally process the massive complexity of modern data. This animated diagram outlines the three-part architecture of a deep learning system. Data enters through the input layer on the left, travels through the dense hidden layers in the center, and reaches a conclusion at the output layer on the right. The input layer's only job is to receive raw, disorganized information. If we are analyzing a photograph, this layer takes in thousands of meaningless, disconnected color pixels. That data then moves into the first hidden layer. Here, the system performs basic mathematical calculations to organize the noise into simple geometric edges and straight lines. As the data pushes deeper into subsequent hidden layers, those basic lines are combined to form recognizable shapes, like triangular ears or circular eyes. Finally, those combined features funnel into the output layer, where the system synthesizes all the previous calculations to produce a definitive result. In this case, the network successfully mapped and identified the physical traits of a cat. The deep in deep learning simply refers to the massive stack of these hidden layers working together to transform raw chaos into comprehension. But how do these hidden layers actually know which patterns to look for without human instruction? They find them through an automated training process. The model is fed millions of examples, and at first it makes millions of incorrect guesses. But every time it makes a mistake, it automatically adjusts its internal mathematical parameters to improve its next attempt. This sheer volume of trial and error requires two things: the massive pools of digital data generated by internet users, and large arrays of highly advanced computer hardware to process it all. Deep learning is the brute force application of scale. You push massive amounts of data through a network at extremely high speeds until accuracy emerges. These hidden layers have pushed AI into the background of everyday life, where it now handles routine operational tasks across nearly every industry. Large language models leverage this deep learning architecture to write original computer code, summarize documents, and translate languages in real time. It is also integrated into critical human infrastructure, helping doctors analyze highly complex medical scans to detect diseases early in life or death scenarios. The ultimate output of deep learning is the automated replication of analytical tasks that previously required highly specialized, costly human experts. However, there is a dangerous friction point built into this system, known as the black box dilemma. Because the hidden layers build and refine their own logic over millions of iterations, human engineers can no longer decipher exactly how the system reaches a specific decision. This opacity creates an immediate ethical risk. If the raw data used to train the system contains historical biases or unfairness, the algorithm will quietly adopt and amplify those flaws without us seeing exactly where it happened. If the internal logic of a machine is invisible, the only way to catch its mistakes is to understand the mechanics of how it learns. We have to be able to audit the output of a system that can no longer explain its own reasoning.